Welcome to the notes for solving 2x2 systems algebraically. Most of this is review for you, so you should remember that you can solve systems three different ways. You can solve them by graphing. We won't spend much time doing that at the moment, but we will do a little bit on the calculator. You can solve it by substitution, and you can solve it by elimination. Your textbook calls elimination linear combinations, so that's something that you might want to know. Elimination in your textbook is called linear combinations. So what we're going to do here is we are going to kind of figure out which way is the best way to go about doing these problems, and then we will solve them. Taking a look at number one, first of all, the bottom equation is not written where the x's and the y's are lined up. So we might want to do that. This looks like it's made pretty well for linear combinations or elimination. However, you could also solve this by using substitution if you let x be equal to 4y minus 21 in the second equation. But we'll do this one using elimination. So you can multiply the top equation by -2, and that would end up working out pretty well. But what I'm going to do is I'm going to multiply the bottom equation by 3. Now notice what that's going to do. What that's going to do is we're going to end up with the top equation being 3x plus 2y equals 7, and the bottom equation will be -3x plus 12y equals 63. The reason why this is called elimination is we're trying to eliminate one of the variables. So notice that the 3x's are now in a spot where they can be eliminated. So if we just add these equations the way that we see them, 3x plus -3x, that goes away. 2y plus 12y is 14y, and 7 plus 63 is 70. Now we solve this and we get y equals 5. Once we get one variable, our objective is to then replace or substitute that variable back into one of the original equations. Usually the originals are better because they don't have bigger numbers after we multiply or something like that. So we're going to take that 5 and we're going to substitute it back into one of the original equations. I'll pick the bottom one. So 4 times 5 is 20. 20 minus x equals 21, so x is going to equal -1 if you solve that. We typically write our final answer as a point, so the answer for number 1 is -1, 5. Sorry, it's a little bit disjointed. The markers are kind of big. If you write with pencil, you can probably fit most things in. So if we look at number 2, what we end up seeing is we have something where we could get y equals 9 halves x plus 5 halves, and then make a substitution. You're dealing with fractions in the short term, but then when you multiply it by 18, you'll get rid of the fractions. So that's an option. I'm not going to do it that way, but again, it's an option to use substitution there. But what I would probably do in this problem is subtract 9x over. So you have -9x plus 2y equals 5. And then we have our other equation, 27x minus 18y equals -21. There are a variety of different ways you can do this. You can multiply the numerator, or the top term, by 3, and then you'll see that the x's will go away. You can multiply the top one by 9, and then the y's can go away. What I'm going to end up doing is I'm actually going to multiply the second equation by 1/3. What that's going to do is it's going to get my number smaller, and then I don't have to do as much work when it's no calculator. So the top one is remaining -9x plus 2y equals 5. The bottom one, after I multiply it by 1/3, becomes 9x minus 6y equals -7. I then solve. I get -4y equals -2. So y equals 1/2. Y equals 1/2. Sorry, that looks like a greater than. Y equals 1/2. Now I'll take that and I'll substitute it in. So I take that y equals 1/2 and I substitute it in. I'll pick the top equation once again. So 2 times 1/2 is 1, and that equals 9x plus 5. I'll subtract 5 and divide by 9, so x equals negative 4/9. So the ordered pair that I will write my answer as is negative 4/9, comma 1/2. One thing that's really important to remember is that all of these things connect. So if I graphed 3x plus 2y equals 7 and 4y minus x equals 21, these lines would intersect at the point negative 1, 5. So one of those lines looks like it's going to have a slope of negative 3/2. So it looks something like this. One of those lines is going to have a slope of 1/4. That's going to look something like this. But in the end, if I graphed those two lines, I would end up with an intersection at negative 1, 5. Same thing in number 2. If I graphed those two lines, I would end up with an intersection at negative 4/9, comma 1/2. I will do number 3 and 4, and then I will let you guys do 5, 6, and 7, and I'll pause the video, and then you can do them, and then you can check your answers. Number 3, you end up with, you could do this in a variety of different ways. If you're going to use linear combinations, I'm going to show you the methodology that you would probably use pretty quick. So if you have this, what you would end up doing here is you would multiply the top equation and the bottom equation by something. So you could, for example, multiply the top equation by 4 and the bottom equation by 9. What that will end up doing is get negative 36y in the top equation and 135 down here. So that'll get positive 36y in the second equation. What will end up happening is the y's will cancel. But notice that sometimes you do have to multiply both equations. I'm not going to do that in this. I mean, it's pretty easy to solve from there. You'd get 75x equals 75. X is going to end up equaling 1. But what I'm going to do is I'm going to show you how to solve by substitution because I haven't done any of that yet. So if I take the top equation, notice that all of these are divisible by 3. So I can rewrite that as x equals 3y minus 5. I will then substitute 3y minus 5 in where x was, in the other equation. You have to make sure you put it into the other equation. So 7 times 3y minus 5 plus 4y equals 15. Notice that when you substitute x, x goes out, and whatever x was comes in. So the goal is to get rid of one of the variables. After I distribute, I get 21y minus 35 plus 4y equals 15. If I simplify, I get 25y on the left. If I add the 35 over, that becomes 50. So y equals 2. And then I'll take that 2 and substitute it back in. Notice if I substitute it into this equation, I get 6 minus 5, which is 1 for x, which was what we would have got if we did elimination. So in this problem, the ordered pair is 1, 2. Number 4. If you do number 4, notice that that looks a little weird. The x's and y's are in the denominator. You'll really want to know this. One way that you can do this problem is treat 1 over x and 1 over y like they are variables. So I'm going to rewrite this as 3 times 1 over x plus 2 times 1 over y equals 17. And then I will rewrite the other one as 5 times 1 over x minus 4 times 1 over y equals negative 12. When I do that, it's pretty easy to see that this is actually just like any of the other problems in terms of linear combinations or elimination. So what I can do is I can multiply the top equation by 2, and notice what's going to happen is my y's are going to end up canceling out. So I'll end up with 6 times 1 over x plus 4 times 1 over y equals 34. And then the bottom equation stays the same. When I add these two together, notice the 1 over y terms cancel. I will end up with 11 times 1 over x equals 22. When I divide, I get 1 over x equals 2. 1 over x equals 2. That's what happens when I divide 22 by 11. So I end up with 1 over x equals 2. Now notice that I can solve this for x, and I can solve this for x by multiplying 2x over to the right and dividing 2 down to the left side. So I get 1/2 equals x. Then I would take that and I would substitute that back in. Or what I could do is just take this 2 and substitute it where 1 over x was. So notice that x equals 1/2, that'll be part of my answer, but I can take that 2, substitute it back into one of the original equations. So I end up with 3 times 1 over x is really 2, so I can replace this with a 2. So it's 3 times 2 is 6, plus 2 times 1 over y equals 17. If I subtract 6 and I divide by 2, I end up with 1 over y equals 11/2, which means y is equal to 2 over 11, because I can multiply the 2 over, divide by 11, and multiply the y over to the other side. So my ordered pair for number 4, and I know this is kind of all over the place, is 1/2, 2 11ths. All right, your responsibility now is to pause the video, try 5, 6, and 7, and then I will be back with answers and interpretation shortly. So if we take a look at 5, 6, and 7, what we see is in number 5, we end up with everything canceling out. So we get 0 equals 0. You can also see something like 4 equals 4 as a potential answer in a problem that looks like this. -8 equals -8. Lots of different things. As long as the numbers are exactly the same on both sides of the equation, what we have to do is we have to consider this as an answer, or as a problem where the lines are actually the same line. So this system actually has infinitely many solutions. A system with infinitely many solutions means that there are infinitely many ordered pairs that make that work. And the reason for that is we would have both equations are actually the same line. And so that is what we call a dependent system. So a dependent system has infinitely many solutions. You end up with something looking like 0 equals 0 or another equivalent. And that happens when you have both lines are exactly the same. Number 6, when we solve, we end up getting 0 equals 30. There are a lot of other ways that you can see something like this, but basically what ends up happening is you end up with two numbers that equal each other that are not the same. So that doesn't make any sense. Clearly 0 doesn't equal 30. So we have to interpret what that means. If we have two lines and they never equal each other, that is what we call an inconsistent system. So that's when we have two lines that never intersect. We call those parallel lines. And so we say that these have no solution. We call those inconsistent systems. So it's no solution, they're parallel, and we see something like 0 equals some other number. Okay, that doesn't obviously make any sense. That leads us to the other vocabulary word, which is independent. Independent are your typical systems where you have one solution. Those are intersecting lines. So those were any problem like 1, 2, 3, 4, and 7. So notice that number 7, you get x equals 0. When you get x equals 0 or y equals 0, that does not mean that it's no solution or infinitely many solutions. These are not dependent or inconsistent. These are independent systems. If you get a variable equals 0, that's actually a number. If you get numbers where all the variables cancel out, that's when we get one of our special cases. So independent systems are problems like 1, 2, 3, 4, and 7 on this worksheet. I just wanted to make sure that it was clear that if you get a value where x or y equals 0, that does not mean that it's dependent or inconsistent. So independent has one solution. They're intersecting lines. And we give those answers as ordered pairs, x comma y. So our answer has to look like an ordered pair in those type of problems. On the back of this worksheet, look at the other video dealing with how to use the calculator to find the intersection of two lines, how to change the graphing window, and how to zoom appropriately.